Hello, welcome back. So starting today, we'll be starting a new section on analytical mechanics or dynamics. And that is built on the idea of generalized coordinates that we discussed before. So I don't think I specifically or explicitly mentioned this before. Let me go back to the idea of generalized coordinates and constraints. So if you remember, we have a system, and instead of describing the system by a bunch of, I don't know, XYZ coordinates, we can describe the system by essentially a long vector of coordinates. So stack all of them together and describe the system as an n-dimensional, the configuration of the system as an n-dimensional point in an n-dimensional configuration space. And we call though the coordinates of that point generalized coordinates. So if we have that, and if the number of degrees of freedom of the system is smaller than the number of generalized coordinates that we are considering, we have essentially some constraint. So if I have n q's generalized coordinates, and my system has certain number of degrees of freedom, then I'm going to need m equals n minus number of degrees of freedom constraints. So these constraints we discussed could be either in very general, separating them into two general categories, could be holonomic constraints and non-holonomic constraints. So holonomic constraints were those that were at position levels, and essentially we could write them as a function of these generalized coordinates and possibly time equals 0. This is a very general form of writing those. And maybe I can give you an example. Let's pretend I have this, I don't know, two-link system, one link here, one link there. And my two generalized coordinates would be theta 1 and theta 2 instead of working with xy positions of these two particles. Let's pretend they are connected with some massless rods to each other and to the ground. So this is a second order 2 degree of freedom system, two generalized coordinates. We don't have any additional constraints, but let me put another constraint here. And for the sake of argument, let's pretend this, the last point, the tip, also moves at some velocity, I don't know, velocity, call it a. So the tip is moving at, on a horizontal plane, for instance. So in this example, the constraint equations would be, I have lengths L1 and L2. So the constraint would be constraint number 1, L1 cosine of theta 1 plus L2 cosine of theta 2. That is the x position of this tip. So this x of tip, which in our case is constrained to move horizontally with some velocity, constant velocity a and at. So the constraint phi 1 of theta 1, theta 2, and t, in this case would be L1 cosine of theta 1 plus L2 cosine theta 2 minus at equals 0. So I had this example because I wanted to show where possibly this explicit notion of time may come into effect in our constraint equations. The other constraint we had was non-holonomic constraints. which were essentially at velocity level, and kind of we show them as phi of q, q dot, and t equals 0 in a very general form. So again, an example would be a wheel. Let me put it like this. I'm looking from the top at the wheel, and the generalized coordinates could be xy position of the center of the wheel and the yaw angle of the wheel itself, named theta. I'm looking from above to a wheel. So in this case, the non-holonomic constraint would be that the velocity perpendicular to the plane of the wheel has to be 0, essentially no sliding of the wheel to the side. So we saw it that it's going to be x dot cosine of theta, the velocity, plus or minus y dot sine of theta equals 0. So this is the constraint that we don't have any sliding. Essentially, the velocity has to, the tangent of, or the direction of the velocity is tangent of theta, or actually the angle of the wheel. And something to note here is that the terms that have velocity, one thing before that, this constraint cannot be reduced to a position vector, because if you want to take essentially an integral of this and get a position level, depending on what value of theta is, which is essentially up to you to decide what value of theta is, and it is completely independent of x dot and y dot. So you cannot take this integral. Depending on the trajectory of theta, the integrated value of this function would be different. So that's why you cannot reduce this to any position level constraint. But anyways, going back, note that these velocity terms, x dot and y dot, show up as a linear term in the constraint equation. So I have x dot multiplied by some function of my generalized coordinates plus y dot multiplied by some another constraint. So for most of the non-holonomic constraint, well, for all of them that I'm aware of, you can write these f as some linear functions a I of q and t times q dot. I is from 1 to n, plus some a t of q and t equals 0. So I can essentially always factor out the velocity terms and work with some other nonlinear function as the coefficient of that. So these a's are just functions of q and t. All right, so I just wanted to be a little explicit about this. Now going back to the idea of relating movement to general coordinates and the concept of virtual displacement. So going back to this example, for instance, the example of a two-link system. Let's pretend I have two particles at the locations of those dots, and those are my particles of interest. So the position are let me see. No, it's good. No, very good. So this position position of particles are essentially some functions of, let's call it I of q and possibly time. And now what I can do is take the differential of this equation. So d ri, and relating the differential to partial differential, I can write it as sum over I over all the dimensions of my generalized coordinates, partial r partial q times dqi plus partial r I partial t dt. So this is the full differential dr expressed as a partial differential along the directions of q. So essentially, this says dr, the actual displacement of one of these particles. If I wiggle around each of these q's, generalized coordinates, how much my particle position changes. So that's what it is. So this is an actual displacement. Actual displacement. Displacement. And we're talking about this physical system with certain constraints. So this actual displacement satisfies, if your system has constraint, has to satisfy the constraints of the system. So essentially these little dq's are not strictly independent of each other if we have constraint, and those dq's satisfy the constraints in their differential form. And to find those, I can take differentials of either holonomic constraint or non-holonomic constraint in this form. So if I have holonomic constraints, I should have this d phi j. I can have multiple constraints, so let's index them with letter j. I'm just taking the differential of this term, phi q and t, and write that as a function of these partial differentials. So this is di phi j over di qi dqi, I from 1 to n, plus di phi j di t dt equals 0. So this is the constraint in a differential form, and the dq's has to satisfy these equations. Or if we have non-holonomic constraint, so let me write this fj as sum of these a, I, but the j version of that, q and t, q dot, I equals 1 to n, this is qi, plus a, t, j, q and t. So instead of q dot, I'm going to write dq over dt, dqi, and then multiply it essentially by dt to write the equation in the differential form. So that would be sigma I equals 1 to n of a I j q and t dqi plus a t j of q and t dt. So the virtual displacement, the actual displacement of the physical system has to satisfy these constraints in differential form, this and that. One thing to note here is that I have these time-dependent terms that, at least the ones I know of, always show up as form of an external effect onto the system. So I showed it here in the top example, where I prescribed the kinematics of this last tip. So it was externally imposed onto the system. And that is how these terms, the explicit functions of time show up. And the actual displacement of a system is required to follow that requirement, to follow all the internal interworking of a system and these externally imposed conditions. To maybe isolate only the internal effects, so internal working and constraints of the system without worrying about these external effects, what we can do is, let's freeze time. So essentially taking dt to be 0. So note that this is not a physical situation. Any displacement in reality takes time. But if we assume that the system moves without any time passing, so this is some kind of imaginary displacement, that's why we call this virtual displacement. And to distinguish it from the actual displacement, I'm going to use this delta notation instead of d. So I'll have dr, or in the generalized coordinate dq. So these are virtual displacement that follow almost the same set of rules, except when time is frozen, dt is 0. So if I go back to my equations and assume this dt is 0, where is the other one here? What I end up with for these equations for virtual displacement, this delta Ri is going to be sum over I equals 1 to n. 1 to n of di Ri partial qi. And instead of dq, I have this notation to emphasize it is a virtual displacement in general coordinates as well. And this virtual displacement, virtual displacements must satisfy the virtual or instantaneous constraint, which in either of the two forms would be either summation of partial phi j partial qi delta qj equals 0 if I have holonomic constraint, or if I have non-holonomic constraint, I equals 1 to n. I equals 1 to n of these functions ai's of q and t delta qi equals 0. So this is the concept of virtual displacement. And I want to emphasize here, they are only different if we have these kind of external effects that is not part of the inherent dynamics of, or the inherent, not dynamics, the constraints within the system. So if I don't have these external effects, essentially time doesn't show up explicitly in my equations, then my virtual and actual displacement are going to be the same, and they follow the same equations for the relationship between R and Qs, and also the same constraint equation. All right, now, one other thing, maybe I mentioned it, we like to work with these virtual displacement as opposed to actual displacement when we are working with in the field of analytical dynamics, because these virtual displacement are how the internal mechanics of whatever system we are dealing with is set up, as opposed to including some external effects. Okay, so now that we have defined virtual displacement, we can take these ideas and go build upon that and talk about topics of virtual work and the rest of the concepts. So until then, I'll see you soon.